One of the more important applications of the chain rule is the implicit differentiation, and that is the topic for this lesson. What is the implicit differentiation? It's a differentiation technique that applies to implicit relations, kind of like this one and that one. And let me show you what these are. And this is going to be an ellipse, and as you can see, this relation fails the vertical line test, which means this curve cannot be expressed as a graph of a function. Same goes this one, which means it is impossible to solve for y and then get y equals to f of x form. Consequently, the usual differentiation technique do not apply here, and then we have to find something else, and that something else is the implicit differentiation technique. Now, we already went through the implicit differentiation technique to calculate the tangent lines and so on, so we are not going to deal with geometrical aspects in this notebook. We're going to use this implicit relation, which is rather dull, as our benchmark. I mean, it is really dull. Let me show you the picture, and it's nothing like the kind of picture we saw before. Not very interesting in terms of geometry, but it gives you simpler computation, which we are gonna badly need later on. So here's the essence of the implicit differentiation. Whenever you take the derivative with respect to y prime pops out. Here's a prime example. Y cubed becomes 3y squared, but y prime popped out. Here, in the product rule part, when you take the derivative by y, well, that should be usually 1, but instead of y prime popped out. The purpose of this lesson is to talk about y, not the cool graphics and tangent lines and things like that. So here we go. If we consider y as not a dependent variable but as a function of x, at least locally, then you can express this original relation into this form as y of x and y of x there. And if you take the derivative with respect to x, then this derivative of y becomes y prime of x. Actually, I think I'd better correct my typo here. And more important part is this one. Y of x, total quantity to the third power. So if you take the derivative with respect to x, then the chain rule applies. 3 comes out as coefficient, subtracting 1 from the power, so we have that. Inside never changes, and by the chain rule we have to multiply the derivative of the inside. Sorry, another typo. Okay, hold on. So y primes are coming from the chain rule, consequently they come only once, and as a result, the resulting implicit differentiation yields a linear equation with respect to y prime. If you have to solve for y prime, that's not going to be too difficult because this is going to be just linear equation. Just take all the y prime terms in one side, everything else to the other side, factor and divide, and then here we go. This is nothing more than standard linear equation technique, except that there are many characters flying around. Still, it's been a long time since I wrote this kind of problem in any exams or quizzes actually. This year may be exception, but I don't know. Okay, the reason I'm talking about this is because I really want to go over to the second derivative. The importance of second derivatives will be discussed in chapter 4, but if we use the kind of technique that we went through only for a tangent line, that is in previous lessons, we could find out all those all those tangent lines and so on, great, but we could not find out the second derivatives that way. That's why I'm bringing this up. As for importance of the second derivative, I think you'll have to wait. That's going to be discussed in chapter 4. In any case, let's go ahead with the computation. Here we go. So, solving for y prime here, if you take the derivative once more, then I'm going to get desired second derivative here in my left hand side, y double prime. The right hand side, on the other hand, will be complicated because we have rather complicated fraction here, even more so. Y and y squared, those are going to be functions, so we'll have more chain rule. Specifically speaking, I'm talking about something like that. I applied quotient rule here, denominator square, and then u prime v minus uv prime, and then whenever you take the derivative by y, y prime popped out here and then there. Now, if you have to express the second derivative in terms of x, y, and y prime, this is sufficient. But if you have to express it in terms of x and y only, not that I'd like to write exam problem like that, but if you have to, then you'll have to plug in this y prime in place of this and that and get something like this, and my goodness, we're gonna get some expression like that. Okay, so let's move on to a little bit more realistic problems. Realistic in a sense that students can actually deal with. Find the second derivative y double prime at the point where x is equal to 1 when x and y satisfy the following equation, and I gave you the same implicit equation here. I think we're safe to simply move on because this is a very same relation. We did implicit differentiation, first derivative, and then the second derivative. That's all done. They weren't easy, but they're all done. But here, if you look at the problem, you're not asked to find out y double prime in terms of x and y symbolically. It asks you to find out y prime value when x equal to 1, so you'll have to plug in x equal to 1. The key is, of course, plugging in the number after taking the derivative, because if you plug in a number in advance and then take the derivative, then, well, the numbers will generate a bunch of zeros because derivative of any constant is 0, so that's not right. So do you plug in x equal to 1 here? But then again, there are so many others. So do you solve for y or y prime there? You don't really have to if you follow a certain algorithmic idea. And that's why I'm bringing this up. This is algorithmic. So go to the original equation, which appear only x and y, and plug in x value to find out y. I don't have any other variables, so this is going to be the easiest way to find out what y is. Once I find out x and y from here, plug both of them to y prime formula and then determine y prime. And finally, plug in x, y, and y prime value to y double prime and then find out the second derivative. If, just if, you have to do this again and take this third derivative, the idea will be actually the same. From here, heaven forbid, you take the quotient rule and chain rule, product rule, and so on to get the third derivative. And then we use the same idea. First one, y, and then the next one, xy, y, xy, y prime, xy, y double prime, and then plug everything to the third derivative. And this can be done algorithmically, and you can determine every nth derivative as a matter of fact if you begin with a certain number. So there is certain importance to this kind of technique, especially you are doing some kind of programming, computer science majors or something like that. In that case, this kind of thing will be important. Otherwise, I don't know if there's any practical use for this. Anyway, let's continue this problem. Plugging in x equals to 1 to the original equation, what we get? Here's the original, right? X is 1, so we have this equation, and then after cancellation we got that. It is important to have 0 in the right hand side, because if I factor, I can set each factor equal to 0. 1 plus y squared can never become 0. So what do we get? Y equals to 0. What do I have? When x equal to 1, as the problem gave you explicitly, we have y equal to 0. So are we ready to plug in both of them to y prime? X equals to 1 and y equal to 0, and punch in the calculator or something, we get -3. And then x equals to 1, y equal to 0, y prime equals to -3 to this y prime formula. Punch in the calculator or something, and we ended up with 0. Not that interesting, but anyway, we got it done. Okay, let's move on to the next section. Another aspect of implicit differentiation. Let's go to the same implicit relationship again, and then let me ask this question. We just apply chain rule to y and considered x as my variable, but why not both? Consider x and y both as functions and apply chain rule to both of them. Basically, I'm asking you to do this. So, applying the implicit differentiation technique to both x and y, x cubed becomes 3x squared, and then x prime popped out, and then the product rule, x prime y plus xy prime, and the y cubed becomes 3y squared, and then y prime popped out. And why is this the case? Well, because we just assumed x and y were both functions of another variable, say t, and t is very typical because that usually represents the time. Then all these are going to be functions. Oops. And then this one and that one will be composite functions. So by the chain rule, we are going to get these x prime, and this one will be product rule, y prime of t, and then finally this one will be chain rule again. And by the same product and chain rule idea, we ended up with the same type of implicit differentiation of both characters. Oops, my mistake. I just wanted to group them together. And this kind of implicit differentiation technique to both characters will turn out to be important when you deal with something called related rates. Now we're going to have a lesson of its own on related rates, and we're going to have some projects on it actually. But it's not going to hurt if you have a little bit of preview. Here it is. If a snowball melts so that its surface area decreases at the rate of something, find the rate at which the diameter decreases when the diameter is 10 centimeters. Okay. So, how do you handle that? As a matter of fact, I just realized that I did this problem with respect to the radius. So, instead of changing all the solution, let me change the problem here with the radius. Decrease it when the radius is now, instead of 10 centimeters, 5 centimeters. Okay, sorry about that, but that's equivalent. So where do we start? We start from area formula for a sphere, s equal to 4 pi r squared, and that's an implicit relationship between s and r. You know what? Snowball is melting and the surface area is decreasing, and consequently this radius is decreasing, so both s and r are going to be changing with respect to time t. So they're going to be functions. So if you apply the derivative, you'll have to apply the implicit differentiation technique to both s and r, and we're going to get s prime. Okay, that part was simple. The right hand side was a little bit harder because we had composite function. So 2 comes out, so we have 8 pi r, and then we have this r prime showing up because of the chain rule. So what we end up with, we have two equations. First equation, second equation, and what kind of unknowns we have. S, R, S prime, and R prime. There are 4 unknowns. Now let's go back to the problem. S prime is given, decreasing at this rate, -1 is given, and radius R, current radius R is given. So we have 2 equations and 4 unknowns. Now we have 2 equations and 2 unknowns because these 2 are given. Plug in those in, and then finish the problem. So S prime is going to be -1, and then we can solve for R prime, and there we go.